So welcome back, Level 2 physicists. We're going to finish off mechanics looking at the concepts around work, power, and energy. And today we're going to look at work and power. So work is done when a force is applied to an object and the object moves in the same direction as that applied force. Okay, so in terms of work, that equals force times displacement. So work equals capital F times D. And the units of work are in joules, force is in newtons, and distance is in meters. Therefore, the units of work are going to be Newton meters, which are the same as joules. So, thinking about it, if a waiter is carrying a heavy food tray across a room, is he doing any work on the tray? The answer is no, because the distance and the force are not in the same direction. So he's not doing any work on that tray. Okay, so thinking about it, in terms of work, there must be a force and there must be a displacement. Okay, and the direction is also critical. So if we look at a couple of examples here, you must use the component of force that is in the same direction as the motion, as we saw in the waiter example. That's the reason why there was no work being done. Okay, so the work in these examples are the force in the x direction times the distance in the x direction, which equals cos theta times the distance d. So if we incorporate an angle, then the work will be, again, force times distance, multiplied this time by cos theta, the angle in this particular case. Okay, theta. And does this always work? Well, think about the example. So we're using the equation that work equals force times distance times cos theta. So in the first example, theta will equal 0, therefore the force cos of 0 will equal the force in the x direction. Whereas if in the other example, the extreme example on the right, if theta equals 90 degrees straight up, then the F cos 90 will equal 0 newtons. Okay, so there is no work being done in the x direction. It's right angles. So in terms of a graph of force against displacement, you will see that in this particular example, you've got a 40 newtons force moving from 2 meters to 8 meters, so a displacement of 6 meters. The work equals force times distance, so that's 40 times 6, or 240 joules. If you look at the graph, the work therefore will be the area underneath the force versus distance curve, as you see. So we've also got the idea of work of a varying force, which we saw on our springs. Okay, so our definition of works only for a constant force or an average force. If the force varies with displacement, as with the stretching you see in springs, what happens? Well, if you plot the force against the distance, you'll get a straight line graph here. And again, the work is the area underneath the graph, so it'll be 10 times 40 divided by 2, or 200 joules. Okay, so power, on the other hand, which is another concept, will equal the rate at which the work is being done, how fast the work is being done. Okay, the more powerful, the faster it's happening. So how do you calculate power? Well, power is going to be work divided by time. So power is capital P, work is given, as we've seen, as capital W, and T is lowercase, time is lowercase t. The units of power are watts, which are essentially joules divided by seconds. So it's the amount of joules being converted by an object every second. So say what? Okay, so we'll look at this more when we look at the electrical systems external later in the year for those who are doing it in semester B. But yeah, those are just examples of some electronic equipment that and their estimated power. So a blender is pretty good at converting electrical energy into blending energy, I guess mechanical energy, whereas a hairdryer is very efficient as converting electrical energy just straight into heat energy. Okay, so that's examples of what that power rating actually means on an electronic device. Okay, so that's probably enough for today when we're looking at work, energy, I guess, and also power.